Now, I don't really like just giving you something to memorize without telling you where it comes from. The proof of this limit actually is in the book. It's a very clever proof. It actually uses some basic geometry, some basic unit circle geometry, but there is one part where they need some calculus, and it's called the Squeeze Theorem. And we don't cover Squeeze Theorem in this class. We just kind of have trimmed it from the course just to make 135 a little bit, you know, you don't really need it. The people who take 135 don't really need Squeeze Theorem. But it is a very interesting theorem. So anyways, the two limits that we want to memorize are the following. So let's say I want the limit, whoops, that's the highlighter. Limit as theta approaches 0 of sine theta over theta. Now, if I were to plug in theta equals 0, what do you get? You get 0 over 0. So this limit, it's not trivial to compute, right? You get 0 over 0. So are you even sure that the limit really even exists? It turns out that the limit doesn't exist. The proof is in the book, and the limit here is 1. And similarly, if I just kind of flip this over, right, if I take the reciprocal of both sides, I get the limit as theta approaches 0 of theta over sine theta. And again, I get 1. Now, I do want to just go over some very common mistakes that are associated to this limit. So the first mistake I want to kind of address is it's something that we actually thought about or did in the very first lecture on algebra, and I gave you those true false statements. You know, so this first mistake is essentially students not working with sine and cosine or just trigonometric functions correctly in general. So a lot of times I'll see some students write something like, oh, sine of 7 theta. Oh, they'll factor out a 7. And then they'll say, okay, sine theta over theta equals 1 or something, you know, and they'll keep going after that. But this is obviously very, very wrong, right? You're not allowed to factor anything inside or outside sine, right? This 7 theta, it's there, it's stuck there. Nothing comes inside sine, nothing comes outside sine, right? You know it's stuck there. And the second major mistake that I see a lot of times is essentially not understanding that this is a limit or not appreciating that this is actually a limit. So I'm going to write a statement, and you're going to tell me why it's wrong. Right? So a lot of times see students write something like sine theta over theta. Oh, that cancels and gives me 1. Look at that dashed line, right, Adam? Remember the dashed line from Notability? Coming in hot there. Yeah, exactly. It's a limit, right? It's very important to understand that we're talking about a limit here. Okay. The limit tells me is if theta is close to 0 but not quite equal to 0, then the values of this expression, sine theta over theta, are close to 1, right? I am not saying that sine theta over theta is equal to 1, right? I mean, if I just put in, say, theta equals pi, I definitely don't get 1. I get 0 over pi, which is 0, right? It's important to understand that we need a limit symbol, right? All right, in the last few minutes, I kind of just want to, well, first, I'm going to give you 2 limits to think about over the weekend, and we'll come back to them on Tuesday's lecture. And then I'm just want to kind of do one last demonstration. So here's kind of an exercise for you guys. So using this limit, try to figure out what do you think is the value of the limit as, say, x approaches 0, sine of 4x over x. And then also think about what is the limit as x approaches 0 of tangent of 8x over sine of 3x. Now I'm going to tell you that the answers are, answer here is 4, and the answer here is 8/3. It's kind of, it looks like it's just the ratio of those two coefficients. But try to figure out how you can figure out that that's the answer using only algebra and these two special limits. Try to figure that out over the weekend, and we'll look at this again on Tuesday's lecture. Okay. And just in the last kind of 2 or 3 minutes, I kind of want to just show you again another Wolfram alpha demonstration. So let's just get a new share here. Okay. Just to kind of bring home this point that sine theta over theta is not equal to 1, right? Let's plot y equals sine x over x. I mean, this is, a bona fide function, right? I mean, its value depends on the value of x. So this is the graph of the function sine of x over x. Right? It's kind of this oscillatory function. In fact, if I were to zoom out a little bit, let's say from x equals negative 3 pi to x equals positive 3 pi, right? I can just type in pi for pi. Actually, let's go even further out. Let's say 6 pi, just so you can really see the oscillation here. Okay, so the function kind of looks like this, right? It kind of oscillates, and those oscillations also die down, right? They get smaller and smaller as you go out. And notice that near x equals 0, even though sine of x over x is undefined at x equals 0, right? There actually is an open hole at x equals 0. But notice that all these values near x equals 0, they all give me a value near y equals 1. So that's why the limit is 1. But in general, the function's not equal to 1. It's not a constant function. It's just that as x approaches 0, I get this value of 1. And there really should be an open circle there, but Wolfram alpha doesn't show it to you. And why they think you would be interested in the arc length of this curve, I have no idea. But... Okay, so that's it for today.